Today we're going to talk about dilations, and dilations are our only non-rigid transformation that we're going to talk about. So a dilation changes the size of the shape, and we talk about scale factor when we talk about dilations. And so if the scale factor is larger than 1, it's an enlargement, and if the scale factor is smaller than 1, it is a reduction. And most of the dilations, actually all of the dilations that we'll do on the coordinate plane are going to be centered, the point of dilation will be at the origin. So, to find the scale factor, you need to look at P and P prime. Oh goodness, I need the pen. So P and P prime. And when we're looking at those, we want to look at P as our image, our pre-image, and P prime as our image. And so we're going from the length 8 from C to P to our length from C to P prime, which is 12. And so we always put where we end up with on the top. So we're going to do 12 over 8 and then simplify. And so this right here is our scale factor, or our K. Okay, and then it asks if it's a reduction or an enlargement. So it's going from P to P prime, and so it's an enlargement because it's getting bigger. Also, because 3/2 is greater than 1. Okay, so this scale factor tells us whether it's an enlargement or a reduction based on whether it's bigger or larger than 1. Okay. On the second one here, we're going from P to P prime, so we're going from 30 to 18, and so 18 goes on the top this time, 30 on the bottom, and I'm going to simplify that, and I get my scale factor of 3/5, and that's a reduction. Okay? So, we can also decide whether it's a reduction or enlargement and talk about scale factor without a picture, without a graph, just by getting some measurements. So the distance from C to P prime is 3, and so that's where we're ending up, and C to P is 12. And so it starts out as 12 and then ends up as 3, that length, that same length after the dilation. And so we're going to do 3 over 12, because we always do the prime length on top, and then we simplify that. And so the scale factor, or the K, is 1/4. And that's a reduction because it's smaller than 1. Okay. When we're on the coordinate plane, we're going to use the origin as our dilation center. And so all we do is multiply the coordinates by the scale factor. So we take K times X and K times Y, and that gives us our new points. Okay, so on here, the first thing we're going to do is we're going to graph A at 2, 1, so 2, 1, B at 4, 1, so this is A and B, and then C at 4, -1, so this is C. Okay, and so here is our triangle. All right, and the dilation is a scale factor of 2, so we are just going to take and multiply each of these points by 2. So we get 4, 2 for A prime. B prime will be 8, 2. And C prime will be 8, -2. Okay, so then I'm going to go ahead and graph those. So I'm going to go to 4, 2, and this is A prime. And B prime is at 8, 2. And C prime is at 8, -2. So our new triangle is twice the size of the original. And so the other thing that I think is really interesting when we're graphing on the coordinate plane when you're doing a dilation, so if the scale factor is 2, so it's double the distance from the origin. So that's why we multiply the points by 2, because we're making it double the distance. And so if you look here, like this distance plus this distance, that's double the original. Okay, and the same would go for all the points. This is half of this. So to get to prime, our enlargement, it's double the distance because the scale factor is 2. Okay. Now we're going to graph this. So we have -3, 6, and that's point K, and 0, 6, which is point L, and 3, 3, which is point M. Okay, and this we are going to actually do a scale factor of 1/3, so it's going to be a reduction. So to do a scale factor of 1/3, you multiply each of the coordinates again by 1/3. So for K, to get K prime, we're going to do 1/3 times -3, which gives you -1, and 1/3 times 6, which is 2. Okay, and then L prime is 0 times 1/3 is 0, and 6 times 1/3 is 2. And M prime, we're going to do 1/3 times 3, and 1/3 times 3, so it's 1 and 1. So now I'm going to graph these. So this is K prime, L prime, and M prime. And so this triangle should be exactly 1/3 the size of the original. And I know it said it on the slide, but I just want to reiterate that they're similar figures. They're going to create similar figures, and that's why we're talking about scale factor, is because we're doing similar figures. Oh, and hey, look, I just made this quadrilateral triangle because I didn't graph point N. I'm sorry. We're just going to leave it at that. It's as it would be another point. You can add it on there, and it is on the notes that I put online. Sorry about that. So, again, these are similar figures. So if you graph a dilation correctly, it will produce a similar figure. So all the angles will be the same. Okay. Sorry that I skipped that and didn't realize it. Okay. Last one here, we're going to do a scale factor of -1/2. And so this will produce something a little different. Okay. So -4, -2, that's our original F. G is -2, +4. And H is -2, -2. Sorry, -2. That's H. So this is our original triangle, okay? If we multiply by a negative, which I also made an error on the notes this time, we still do the same thing. So we're multiplying all the numbers in the points by -1/2. So F prime would become 2 and 1, because -1/2 times -4 gives us 2, and -1/2 times -2 gives us 1. G prime will become -1/2 times -2 is 1, and then -2, and then H prime is 1, 1. So I'm going to graph these, 2, 1, 1, -2, and 1, 1. And so this triangle is going to be similar to this triangle, and it's just orientation has flipped. Okay, so if you have a negative when you're doing a dilation, it changes the orientation as well as the size. Okay. All right, we're going to do one more. For this one, what I would recommend is if you have a piece of graph paper, that you get out a piece of graph paper and you try this on your own. Okay, so for triangle PQR, graph the points P, Q, and R, and then try and do the dilation with a scale factor of -2, and let me do it here for you. So pause this and then check your answers with what I have. Okay, so when you graph PQR, the original, it should be here. And then P prime, Q prime, R prime should be here, and I've written the coordinates over here. So it's been rotated 180 degrees because that orientation changes because it's a negative dilation. and it is double the size of the original, but they are still similar figures, so they should still have the same shape and the same angle measures if you were to measure the angles, but it's larger than the original. And right now, I am throwing an extra credit opportunity. Email me and tell me where you would go on vacation if you could take a week-long vacation right now. So if you could go on vacation right now, where would you go for a week? And I tell you what, I would go somewhere warm where I could be out on a beach without a mask on, because it would be really nice to be in the sunshine given the current weather. Okay, back to this. Suppose a figure containing the origin is dilated. Why is the corresponding point in the image of the figure also the origin? Well, because the origin is 0, 0. Okay, if we multiply 0 by anything, doesn't matter what the scale factor is, enlarged, reduction, it's still going to be 0, because 0 times anything is 0. So it will stay 0, 0. All right. One last one that doesn't have to do with a graph, and it doesn't have to do with a diagram. So it says you're making your own photo stickers, which we all love photo stickers and stickers in general. It's 4 inches by 4 inches, and the image on the sticker is 1.1 by 1.1. What is the scale factor? So we're going from your photo to the stickers, and so the stickers size would go on top. So this is going to be our scale factor, and I'm going to turn it into a fraction. So the scale factor is 11 over 40. If you want to tell me the scale factor is a decimal, if you're given a decimal, that's okay too. So you could say it is 0.275, and it is a reduction because this scale factor is less than 1. Okay. All right. Last thing is, how are dilations alike and different from rigid transformations? So dilations are different because they produce a different size figure. So it's either enlarging or reducing. And so if we do a translation, a rotation, a reflection, they're all going to create congruent figures. Dilations do not create congruent figures. Okay? But they're similar because they don't change the shape. So even though it's larger or smaller, it's still the same shape. They're similar figures. It produces a similar figure instead of a congruent figure, but it's still the same shape, just a different size. Please let me know if you have questions. Otherwise, go ahead and complete that dilations assignment, and I will see you next time.